Can you see my screen now?
Yes. Do you want to make them full screen?
Yes. All right. So let me jump in directly. Our group with Ala Karnowski, who is presenting tomorrow, sort of a summary of our contributions throughout this project. We have focused on developing methods and tools for data-driven construction of networks for related groups of samples based on expression data. Our focus has been on metabolomics data, but the tools and techniques definitely work with transcriptomic or proteomic data. And at the deep down at the technical level, what we have leveraged is concepts and techniques from what is known as graphical models. And in the estimated network that we get from this expression data, the nodes correspond to metabolites, and the edges capture some notion of statistical association, either correlations or in our case, partial correlations between them. However, there has been a number of efforts in the literature, but many methods or tools have focused only on two groups of samples, let's say healthy and disease samples. And the number of methods are not very straightforward to extend available methods to extend to many more groups. So the focus of this work has been how to develop methods that for multiple groups that also can take a lot of prior information. So the moment you mention prior information, it's natural to go to a Bayesian technical framework where you can incorporate prior information or encode prior information, both about the experimental design and also information that may be available in the literature about presence of particular edges through the prior distribution. And the other big contribution is that for each group of samples, every network is assumed to be decomposed in a idiosyncratic, what we call idiosyncratic component, but is very group specific and also share components with other groups. However, although you can incorporate this prior information, more importantly, the search over these shared components is done in a supervised way and primarily leveraging the evidence in the data. The other big advantage of the Bayesian framework is that for every edge that your method estimates, you can also get a notion of uncertainty. Think of the equivalent of a confidence interval in a more classical frequency setting. Just to illustrate what I mean by this decomposition to idiosyncratic and shared component, here I have a toy simulated data. What you see is the heat map of the connectivity network metrics for 4 groups. And you can see that for this group, let's say of metabolites, there is a shared pattern. Whereas for this group of metabolites, there is a shared pattern between 2 other groups. So essentially that's what the shared components in these decompositions are trying to accomplish and essentially find both idiosyncratic and shared components. As an application, we downloaded some data from the Metabolomics workbench. So essentially we have 4 groups. That's sort of, you can think of it as the underlying experimental design. You have patients with IBD and you have non-IBD controls, and also you can break them in males and females. The key thing is that using the nomenclature that group 1 are the males with IBD, group 2 the females with IBD, and so on and so forth, I incorporated a little bit of information from the experimental design because there might be shared components between males and females with IBD or males between the controls and the IBD patients. And of course, there can be a shared component where essentially all the groups share the same number of edges. That's what I mean by a component. In the interest of time, here I'm showing you some examples. I have some comments. What we see by just using this methodology and the data, we see that there is a very large number of edges that form a common backbone of the network because they are shared across all groups. And also we see that the component share between males and females IBD patients is very well connected. The other advantage of Bayesian methods is that you get this type of results. So for every edge that corresponds to a connection between 2 metabolites or a lipid and a metabolite and so forth, you get these probabilities of whether this edge was present or not. Here we see that it was not present, or how strongly it was present in a particular shared component. Here I'm showing you the backbone networks that showed up as common across all 4 groups, and I broke them into primary metabolites, secondary metabolites for ease of visualization. And there are some remarks that in the interest of time, I'm going to skip. And the very technical paper, there are a lot of technicalities. If you are interested, I can definitely send it to you. More importantly, we have our code as a wrapper around C++ implementation, because as every Bayesian method, this is computationally fairly expensive. And thanks to NIH for financial support. And definitely, if anybody's interested in trying this method, please contact me. We haven't written yet a manual of the R code, so there might be some issues that I need to explain to future users. Thank you very much.
Thank you, George.